All right, so today's conversation, we're just going to go over two situations specifically that extend Young's double slit experiment, and then we're just going to do problems the rest of the time. So this actual lecture part is going to be pretty darn close. So we actually already started the lecture. I didn't know more before, so we'll talk about it very, very briefly for the sake of the video, but then we're going to go back to it. All right, here's the gist. In a nutshell, again, we will use this in class here to review real quick. All right, so we have a source. It's going to put out rays in every single direction. Specifically, one of those directions being the red line headed towards P. The reason we chose P is that if you look at the blue line is hitting the mirror such that it follows the law of reflection and uses the same angle in as the same angle out, just like all that stuff we talked about last chapter. And the blue line should hit at point P. That's why they chose the red line to also hit at point P. It wasn't just a random location. Okay? So if you follow the blue line, it's going to bounce off and go towards point P, but if you trace it all the way back, we can kind of approximate it as though it is this source S prime in the bottom. And so now we have two sources, each of which have traveled different distances. So it's operating very similar to what experiment? Young's double slit experiment, exactly. So we can use a lot of similar math. The one thing that is different in this particular case versus the Young's double slit experiment, even though the math is exactly the same, is the fact that we have to deal with, right here, reflection occurs. And just like we talked about in the low reflection chapter, if we have reflection or a wave travels into a fixed boundary, what should it do? It should invert. Okay, so if we draw a picture here, if I draw a wave, we know from Young's double slit experiment, if it goes the same distance, we should get constructive interference because it's in phase. Or if we have extra, we have to have a extra by some integer number of wavelengths. 1, 2, 3, or 4, that's what M is. M is never a non-integer in order to get that extra. The difference in this case happens due to the reflection that occurs at a fixed boundary, which, if you look at the picture on the last slide, this is. We'll talk about how I know it's a fixed boundary and not a free boundary in just a second. Okay, the fixed boundary means it will invert, just like we talked about the other day. So if it inverts, if we go back to this picture, you can kind of think of this bottom wave. We'll go ahead and start them from the exact same spot again. As right here, let's say it hits at that particular spot, you can kind of think of it as, at that point in time, taking the wave that would be and inverting it. Let's actually go a dotted line here. So now that you see that if they do in fact travel the exact same distance, are we going to get constructive? Nope. So in order to get constructive, what do we need to have this bottom ray do? Add an extra half a wavelength in order to get constructive interference. So your basic gist is the equations for Young's double slit were this: d sine theta equals m lambda gives us constructive interference, and d sine theta equals m plus 1/2 lambda gave us deconstructive interference due to reasons we talked about. But in this case, basically, they are flipped. Instead of going a half a wavelength more to get destructive interference, due to this reflection that occurs right there, we have to go another half a wavelength. Here it is, the half a wavelength to get to the top part once again. Or we can do another extra one. And this m in this case is how many extras, because you'll notice in the first case, if I distribute this out, instead of this being what it looks like, we just say lambda times m plus 1/2 lambda. What we really need is the extra half, and this is how many are extra. So in this case, where I just draw 1/2, m would be 0. If I draw another wavelength right there, m would be 1, and then 2, and then 3, and then 4, and so on and so forth. Yes? Cool beans. Now, how do I know fixed boundary, free boundary? Well, you'll remember we talked about that interference occurs when we go to a different medium. And the different medium we're referring to here can really be noticed well by the n value, right? What happens when the n value increases?
Higher refractive.
What's that?
Higher
Yeah, and which means what? The higher index of refraction means slows down. So this is like running into something like a wall. So going from a lower index of refraction to a higher one, like going from air to, say, water, or air to glass, would serve as a fixed boundary, because you can kind of think about these don't move very much relative to all of these over here, and vice versa. If we have a situation where the ray goes from inside glass or inside water, aka you're sitting inside of a pool you've dove in and you're looking out of the pool, okay? If you're dealing with that, well then, because these move very freely and the inside don't, it's a matter of free boundary. Now, what does that mean to you? What it means is we just go back to the Young's double slit experiment, because it is not the situation where it reflects right here. Instead, it's once again the situation where they have traveled the exact same distance. It's kind of like if we think about reflection, it's going to come back the opposite way. As a matter of fact, that's probably not a bad idea. Let's do this. Okay. If I hit a mirror with glass, then what this is going to do is invert back the opposite way, right? Whereas if I am already in glass and I hit air, this ray, which came in like this, is going to, using an entirely different color, it's going to be reflected back, but it's not going to be inverted, right? So it's kind of as though it just continued on entirely like normal. Does that make sense? All right. Next, interference in thin films. Okay, an interference in a thin film is going to be, once again, very, very, very similar to what we were just discussing. Okay, it's the exact same math. And a matter of fact, it's the exact same principles as what we were talking about a second ago. So imagine, if you will, you have this. Okay, we have this ray coming in, okay, from outside, right? And as we've always talked about, it's going to do two things. What's one of the things? Well, it's going to reflect, right? Since it just reflected, and you'll notice that this is some solid that is not air, should it invert or should it stay the same? Or another way to say that is, does the phase stay the same? Does it stay like it was, or does it phase change 180 degrees? Phase changes, correct. So you'll notice, like it says right here, that this guy has phase change. Okay. Now, if, watch here carefully, let's say this was an n of 2, and this was an n of 3. It's not, but let's say it was. Here you'll notice this is always an n of 1. Here, since it goes from low to high, it's like a fixed boundary, right? So that's why it phase changes. By the way, this only works on reflection, not refraction. Okay? So if this was the case, when this refracted ray, no effect yet, comes down and reflects, if it was 3, it would also be a fixed boundary, which would mean that would there be a phase change? Yes. So when it came up here, what you'll notice is, have these two rays, 1 and 2, traveled a different amount of distance? Yes. Yes. So as long as that difference of distance is, if both of them change phase, who the heck cares? It doesn't have any impact on what it previously did, because what it looks like is this. If both of them phase change, it would be like, here. We have a ray coming in, okay? Ray coming in, and here, instead of, actually, we'll start at the top right here. Let's start right here. Instead of being this when it inverts, it of course just flips sides. I thought that was a different color. It flips sides. But the thing is, if I have another ray do that exact same thing, does it have any impact whatsoever? No. So now we're back to the old situation. When are we going to get constructive? When we are at multiples of the wavelength. When are we going to get destructive? At the 1/2 the wavelength. Make sense? But if we go here, like the picture they originally drew, I'd like the eraser. No? In the picture they originally drew, this was not the case. It said air, glass, air. So as it moves from air to glass, that would be a fixed boundary, and so yep, there should be a phase change. But when it comes down here and reflects again, why is there no phase change? It's a free boundary, so it doesn't invert. So now you've got this guy who's traveled a different distance with no phase change. Since there is no phase change, I'll get to that in just a second. Since there's no phase change, to get constructive interference, we are back at the 1/2 to be off. This is just the same as the reflection issue we had earlier. So here's the situations we have. Okay, in Young's double slit experiment, it's just standard. Okay, these two hit, so they are automatically in phase. They have to start in phase. That's the whole coherence conversation at the very beginning. So if I want them to stay in phase or construct, I either have to have them go the same distance, or I have to have one go an extra distance. What we added today is that now, okay, I've got two rays. Okay, stop up here. This one hits a mirror, so it inverts. So now what's the problem if they go the same distance? Destructive interference. So if I don't want them to go the same distance, I need to let one of them go 1/2 of a wavelength more, or some other multiple plus 1/2 of a wavelength more. Yes? That's exactly what happened here. This guy flipped. This guy didn't flip. So they need to be off by 1/2 in order to get constructive, and off by a multiple in order to get destructive.
Can you explain again why the other one doesn't flip, like the no phase
It's the
change?
boundary situation that we saw back on this guy right here. Remember when we talked about fixed boundaries and free boundaries, right? That's this guy, the spring was a fixed boundary. So you saw a wave go in and it inverted. But if there was a free boundary, meaning instead of that wave kind of hitting a fixed point, let's say there was somebody with their hand back there that could nicely match exactly what wave is coming in, it does not invert. It gets reflected back, but it stays on the exact same size, right? This, when we go from a low end value to a high end value, is like these guys don't move, so that's fixed. But if we go from a higher end value to a low one, like I said, like being in a pool, right? Inside a pool, looking up, obviously, hold your breath or whatever, but looking up, that's like light traveling from a higher end value to a lower end value. And in this case, think of these guys as being free moving, and this one not being very moving. So it's a free boundary. So since it is a free boundary, it doesn't flip, aka there is no phase change. Does that make sense?
Yes.
Okay. Phase change in the degrees is a little bit confusing. Okay? Degrees and radians are actually used to measure kind of like percentages of a cycle, because there's a lot of math that works a lot easier for. Okay? It's basically like this though. Okay, we just draw a very similar, like if something's going in a cycle, I'll draw a visual of an object going in a cycle. Here it is. Okay, this person's going in a circle, or the Earth is going around whatever. Essentially, what they do is, if I said, "Hey, you've gone through a quarter of a cycle," you would say, "Well, they've gone through about 25%." Yes. Okay, and half the cycle would be at would be 50%. That's oftentimes what we would use. How much of the thing they've gone through. In other words, if you have a nephew on the swing, okay, they start back here. When they're over here, how much of the cycle have they gone through?
One.
No, They've gone through half. Then they come all the way back. How much have they gone through? No.
Oh, 1.
Oh, yes, right. From the very beginning. Yes, that's on me. From the very beginning. All we do when talking about angle is we associate angle with percentage, right? So if I say 0%, it's like saying 0 degrees. That also means in phase. This could also, of course, be 360 degrees. They are in phase. 360 would be like if the kid has started here, gone here, gone here, gone here, gone here, and come back, and then his brother starts at the exact same time he is back. He has gone through one last cycle, but they are in phase together. Yes? So if I say 180 degrees out of phase, all I'm saying is that it's 50% of the cycle later. Okay? It's a weird thing to imagine, but if you could invert like the nephew, what would happen is that the nephew would like be going back and forth, back and forth, back and forth, and they would hit back here and teleport over there and be headed back the opposite way. Okay? A little bit weird to think about, but that is sort of what would happen. To be fair, kind of morbid here, but this does work, actually. Okay? Imagine that your nephew is going back and forth, going back and forth, going back and forth, and you have a superpower, the ability to materialize a concrete wall wherever you would like, aka a fixed boundary, right? So here they are, back and forth, and imagine you materialize a concrete wall right here. What's going to happen to them when they hit? They're going to immediately go back that way, especially if they're particularly bouncy, as we'd like to imagine for this particular case. Have they just switched phases 180 degrees? Yes, because half the cycle later is them going the other direction. All right.
Still less morbid than the child hill.
There's a lot of morbid stuff we talk about in here. All right. So, Morgan, does that answer your question on why it doesn't change phases down here? So I tried to use an example early on where, let's say, there was a third material, like it was like air, glass, and like oil or something like that. In which case, if it was going from glass to oil, there would be another phase change, and has increased. All right. Now, a couple things to address in this particular equation that makes the thin lenses a little bit different. For starters, you do have to remember that we have been using this equation, we've been using lambda to talk about how different. Well, if you remember from last chapter, what happens to lambda when you enter into a material?
It
decreases, it changes. So we have to address that. So where it would have been this equation, d sine theta equals m lambda, right? Well, lambda is going to slow by the value of n, because the velocity is also slowing by that value, right? So if I rework this equation, lambda is equal to n times wavelength n, where wavelength n is the new wavelength inside that material, right? So if I take this equation and replace this with n times lambda, you get this guy right here. Actually, I screwed up because I forgot the 1/2 part, but there it is. Now, what is this 2t? Well, this only occurs because they are traveling a different distance. How much distance is different between this guy and this guy? Well, let's say both of those from that point on is the same amount. Yes? So how much is extra? 1t, 2t. Now, if you're a little bit kind of carefully go, wait, with the geometry isn't technically, this is absolutely a very, very, very blown up picture. Because remember, we're looking at a thin lens or a thin mirror, meaning the thickness of this right here is the thickness of that bubble. Okay? So, is it fair to say that, so like this is air on the outside, light comes in, hits the bubble, goes through thickness, and then there's air inside, right? What we're talking about right now is the reason for these crazy colors on here. These crazy colors are interference patterns, areas of high concentration and low concentration due to having this kind of in the mirror right there. So when I talk about a thickness of this t is not very big. So is it probably very fair to say that thickness is the actual approximation of how much distance it's going to go? Yeah. This angle is actually probably closer to something like this, right? So it's going to go 1t, 2t, and then they're going to be going the same direction again. Yes? So what we said is, what this equation says is, all right, you get one phase, no phase change, so we have to be off by a half. That's the reason for this piece, right? This guy changed because the wavelength changed inside the particular material. And we get constructive interference when this occurs, when the difference between the distances is this, and this guy, little guy right here, is the difference of that distance. Does that make sense? Let's go one more time. Okay, it hits and inverts. Yes, but it also would keep going because it refracts, hits down here. It does not invert. So now we've got a pattern. It will be constructive when it's off by 1/2 of the wavelength plus some extra. Who cares how much is extra, right? That's when you're going to get constructive interference. Except this wavelength is the wavelength in a vacuum. So since this is occurring inside here, we need to use the wavelength inside that medium. So instead of wavelength, we're going to use n times the wavelength right there to get that particular value. Cool with that? Okay? And this has to be equal to however much extra these two rays have gone. How much extra has 2 gone relative to 1? It went 1 thickness, 2 thickness, where the thickness is the distance from one side to the other of the material. How we doing?
I think I'm only still confused as to what the wavelength and just the wavelength inside of that thickness.
Correct.
Okay.
This thickness is where it's getting the extra distance. Yes? So if we want to calculate that distance, we should use how far the wavelength is going inside that particular material. Gross dramatization here, but if this is the normal wavelength out in air, it doesn't make sense to use it when it's inside the material. We should use the wavelength inside the material. And what is index of refraction? Index of refraction is how much the velocity slows down inside the material. Right? And why does it slow down? It slows down because it's enter and that type of thing, but frequency doesn't change. And remember, velocity is equal to this would be the frequency of the material times the frequency, because velocity is equal to wavelength times frequency. And this is equal to wavelength outside times frequency, right? And notice in that equation what happens to frequency since it's the same in both spots. AKA, we can say, if the velocity cut in half because of the material, or n would be 2 in that case, then the wavelength cut in half inside of there. So that's why we need to use the new wavelength for that case. Now, that is all to say, here's your new equation. Instead of putting wavelength of n, in this case, okay, I don't want to use wavelength of n, I'm just going to substitute this in right here and use, this is wavelength the outside one divided by n. So now I don't have to recalculate the wavelength at all. I can just use the wavelength coming in from air. Technically divided by n would give me that wavelength that I need. And let's rearrange it. Let's go ahead and just put n over here on the left side. And this says that the difference of material is equal to the destructive interference due to the phase change in this case. Still writing that down. See a couple of here. Jordan, here's my struggle with the computer. Ain't no way you wrote all of those symbols and weird things down on the computer in the amount of time that would allow you to also pay attention. It doesn't make sense not to use paper in this. It just doesn't make sense. All right. That equation is dead wrong. I need to change it like now. All right, let me change that last one. What they're trying to show you right now is that this will get you constructive interference. So as you would probably guess, kind of inverting it again, destructive interference, what this should say right down here is 2nt, the difference between those rays, when it's equal to this, where n is 0, 1, and 2, that equation will get you destructive interference in this case. That being said, okay, this is what we were kind of talking about earlier. That last example, it's, hey, this hits a surface. So right here, inverted or not? Inverted. Because it's hitting sort of a fixed boundary. It's going into something that is solid. Invert or not? No. Because?
It goes from
Free boundary.
high to
Go to
low.
a free boundary. Correct. So that's why we got one phase change and not another. Okay? On the other hand, this is what I was trying to talk about a minute ago. I forgot that it was over here. Let's say instead of going air, material, air, you go air, material, different material. In this particular case, here we go. We got air going into an n value that's higher than 1, so invert or no? Invert, so there's a phase change. And then we come down here, and some refracts, who cares? All we care about is the amount that reflects, right here, inverted or not, inverted again. So they both invert, so that's like this. Here they are, they're going along, they're going along, they're going along, and right here they invert, so they both invert. Are they still technically with each other?
Yes.
Yes. So they're definitely going to travel, unlike Young's double slit experiment where they can travel the same distance. Is it possible at all for these to travel the same distance? No, they're going to be off by 2t. One t down and the other t back. So here we go, they're together. So how much further does this guy have to go over here to be in phase? 1 wavelength, or 2 wavelengths, or 3 wavelengths, or 4, and that also will be equal to, yes, 2t in that particular case. All right. I believe, yeah, I'm not going to talk about Newton's rings right now. I'm not going to talk about Newton's rings at all, but this is what I wanted to get to. So this works for the double slit stuff, but it also works a ton for other things as well. So we've discussed Young's double slit experiment today. We've discussed reflection today, like if it's just basically Young's double slit, but instead of dealing with double slit, we've got one ray leaving a source and the other like bounces down into water and comes back up. But similar to that, we have the thin film reference. And the first thing you've got to do is please, please, please draw a picture. Please draw a picture for the purpose of kind of, basically when I draw a picture, here's what I draw. And I'll show you what I'm looking for. In these situations, if you see it occur, I'm doing this, I'm doing this, okay? And what I'm looking for very carefully is there's going to be reflection, Is there a phase change or not? Is there a phase change or not? Yes? This just kind of puts all of that on a slide. If there is 0 or 2 phase reversals, 0 means here they go together, no phase reversals whatsoever. So what do they need for constructive? To go a magnitude over. So for 0 or 2, sorry, let's go. You notice that this equation, extra by that, will get us constructive, right? Whereas, I don't love the way they ordered this, by the way, because I'm starting on the, my apologies, but starting on the bottom right there. But now going to the right upper top of that. What if I have 0 or 2? Well, by the way, I just did 0. There's 0, 1 extra, 2 extra, you get it. Okay, but what about 2 phase reversals? Here they are. Same thing, right? But what if it's 1 phase reversal? Well, if it's 1 phase reversal, then we have this. Here they go together, here they go together, here they go together. Flip. So right now, okay, let's stop it. How much extra does this guy need to go to get constructive interference? Half more, which is why at 1 phase reversal, constructive will occur with that equation right there, where it was destructive for the other. Yes? Cool with that? And finally, 1 phase reversal. When are we going to use this equation? When, here we are, 1 phase reversal, up and down, up and down, up and down, flip. Well, we're going to get destructive when it is either 0, 1, or 2, or 3. Make sense? All right. Use the remaining half of the class period to work on the homework that goes with this. I believe what I have just done has covered practically 80% of the homework in this chapter. So, if you're not good at it, let's use this time to practice. And that's it for me.